Arnout Everts is a broad-skilled geoscientist holding a Ph.D. in earth sciences and 30-plus years of industry experience in oil and gas exploration and development, commercial advisory, reserves and resources certification, geothermal resources, and data analytics. He has participated and led over 100 energy projects spanning the entire project lifecycle from frontier exploration to unconventionals such as coal-bed-methane and in recent years geothermal energy, CO2 storage and natural hydrogen. This is the Energy Newsbiz interview series. To support it, please check out our advertising options in the description. Thank you. And now, here's Arnout Everts. Who is Arnout Everts?
I'm a geoscientist, so geologist by background. I have a PhD in earth sciences from the University of Amsterdam, and I have 30 years plus experience in the oil and gas industry. And a lot of my experiences is consulting and assessments of what's called reserves and resources of oil and gas, but more recently of renewables, including geothermal energy. I've also looked a fair bit at so-called resource plays like coal-bed-methane, and now I'm also very interested by the reports about natural hydrogen and the potential that this may have to basically facilitate some of the energy transition.
Tell me what indicators suggest the emergence of abundant white hydrogen in the market, and can you elaborate on the recent findings?
Yeah, it's a very good question. I think the interest in natural hydrogen has been spurred by a couple of things. First of all, by the recognition that hydrogen, as a clean, emission-free energy source, could play a pivotal role in energy transition, but that's mostly as a medium to store excess energy from renewables like wind and solar, but also to basically decarbonize very energy intense processes like steel plants, but also in future maybe aviation. Now, in the context of all that, people have also started to relook at natural occurrences of hydrogen. Hydrogen was always believed to be very scarce as a pure molecular substance in nature because they're very small molecules and highly reactive, so they react with other common elements like with oxygen to form water or with carbon to form methane. But some natural hydrogen has been reported in historically, actually as old as more than 1,000 years ago, and a couple of some 15 years ago, an instance in Mali in Africa where during drilling of a shallow water well, shallow gas was encountered, leading to an explosion, and they found that this was hydrogen. And this hydrogen well, which is called the well is called Bugu One, has since been hooked up to a generator providing power to a nearby village, so powering some houses and a bakery or so. But that find and the recognition that maybe there might be more hydrogen out there that could be harvested from nature rather than producing hydrogen from very energy intense processes has spurred the interest in natural hydrogen. Now, there are some estimates around from studies by the US Geological Survey and others that suggest that the Earth's crust emits significant quantities of hydrogen, possibly in the order of 23 million tons or more per annum. And that could be significant, although it's not as much as the current world consumption of hydrogen, which is close to 100 million ton and likely to increase. But maybe there could be more out there. I guess I'll leave it at that for now.
Could you elaborate on the challenges and considerations in the research and exploration of natural hydrogen and why it's essential to add the context?
Yeah, also a very good question. Um, I think it's important to recognize recognize that whilst indeed the Earth may emit significant quantities of natural hydrogen, most of these emissions are what people would call highly diffuse, which means that they're spread over large areas, and they're what people geologists would call natural seeps at low flow rates, rather than trapping of hydrogen at excess pressure in hydrogen fields similar to natural oil and gas, which is typically trapped in a porous and permeable reservoir at excess pressure. So it has been accumulating there over hundreds of thousands or even millions of years. And it doesn't escape because it's trapped underneath the seal. Uh, these kind of settings, the gas builds up a lot of pressure, which means that if you drill a well in it, then this pressure uh, 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 causes the gas to then expand when you drill the well, and this expansion creates energy and makes the gas flow into the well. The natural hydrogen occurrences that have been reported so far, it looks like no equivalence to the natural gas field trapping of gas have been found. It's possible that these kind of settings exist, but most of the things found so far look like natural seeps, like the one in Mali. Uh, exploiting these might be possible, but production rates will be low. So a key challenge to uh, um, commercialization of natural hydrogen is to find settings where production rates can be scaled up to the magnitudes that people are used to for natural gas fields. Now, another possible setting where hydrogen occurs is hydrogen adsorbed in coals. A recent report of a hydrogen find in France in the Lorraine Basin, which is an old coal mining area, uh, um, kind of gives rise to the thought that there could be more areas like that out there where hydrogen is absorbed in the in coals and can then be produced by drilling wells into the coals and withdrawing pressure. This is similar to the concept of producing what's called coal-bed-methane, which is essentially mine gas, but where instead of mining the coal and then bleeding off the gas first to basically minimize safety risks, is you actually produce the gas. But with coal with methane and with coal from hydrogen, the situation is likely similar. Flow rates again will be low, and you would be looking at drilling very dense grids of very low cost wells, all producing at low rates. And whilst hydrogen has the advantage of being an emission-free energy source, the concept of drilling dense grids of hundreds or even thousands of wells may not be so attractive from an environmental perspective. And another challenge with uh, producing gas, be it natural gas or hydrogen from coals, is that the gas comes with lots of water, which you would have to dispose of in an environmentally acceptable way. And then a final challenge might be that rocks like coals are typically quite low permeability, they're very tight, and to flow a gas from them, uh, especially if the coals are buried deeper, you will be looking at some sort of stimulation. And the most common form of stimulation is called fracking. And I think everyone who's heard about tight gas will know the issues with fracking and the concerns from an environmental perspective because of the huge amount of water that are required, which will then be contaminated, and also issues potentially fracking into shallow aquifers and also all of this.
How do the properties of hydrogen contribute to the scarcity of subsurface occurrences? And what role does binding with other elements play?
Okay, another good question. Like I explained already, hydrogen is a very small molecule. It's the lightest element on Earth, and it's extremely reactive, much more than hydrocarbon gas. it tends to bind itself to other elements, so to oxygen resulting in water, and to carbon resulting in methane. And um, this uh, binding to other elements, and therefore kind of losing hydrogen on the way, could happen either during migration from a source where the hydrogen is generated to a potential reservoir where hydrogen might be trapped at excess pressure, or in the reservoir itself. And in petroleum systems, so oil and gas, migration from the source to a reservoir typically takes hundreds of thousands or even millions of years, very long time. So if the same would apply to hydrogen systems, then the risk of losing material quantities of hydrogen because of binding to other elements, and generating water or methane, would be substantial. So therefore, conceptually, um, um, hydrogen traps might have to be located very close to the source of the hydrogen to avoid kind of a very significant dilution. Hope
Can you
that's clear.
explain can you explain the geological processes behind hydrothermal alteration of ultramafic rocks and its role in releasing hydrogen?
Yeah, I will do so. Um, what's called ultramafic rocks. These are rocks that are very rich in iron and magnesium silicate minerals like olivine and pyroxene. Now, this is very technical terms, but for a layman, a typical ultramafic basement rock is the rocks that are formed on the seabed. Now, if these kind of rocks on the seabed are uh, interact with water, um, and they then chemically change. This process is called hydrothermal alteration. That's just a technical term for rock interacting with water, and chemically changing. Um, with these iron-rich rocks, there is a contact with water induces a process that's called serpentinization, which basically oxidizes the iron and magnesium silicates, and it releases hydrogen. Now, where these kind of rocks are very common, which would be on the seafloor, and especially around mid-oceanic reaches where these rocks are newly formed, there this serpentinization is quite common, and it's known that hydrogen is generated there. But obviously, the rock is on the seabed, so there's nothing to trap the hydrogen. So we would be looking for situations where these kind of rocks occur, but now buried by other rocks, but still being brought in contact with water, and hence generating hydrogen. And then this hydrogen, rather than escaping to surface, being trapped. Now, these kind of settings could exist in nature, but they're not very common. Maybe they are more common than geologists currently think, but it requires a very dedicated type of exploration. Another problem with this would be that um, those kind of settings where ocean rocks originating from the ocean floor now are buried in the subsurface and maybe incorporated in a mountain range or so. These kind of settings are not typically the settings where you expect also very huge areas with pores and permeable reservoirs in which you can trap huge amounts of of the hydrogen that's generated. That's not to say that it can't happen. It's just that it from what we understand about the geology of the Earth, this is not a very typical type of setting.
Are there alternative sources of subsurface hydrogen, such as radiolysis or degassing, and how significant are they compared to hydrothermal alteration?
Yeah, there are other processes that could generate hydrogen in the subsurface. One process is called radiolysis. What this is if you have rocks that have an unusually high amount of minerals with radioactive isotopes, and these isotopes could be uranium, so a uranium-rich granite of some sort, then these isotopes, they decay over time, and as they decay, they generate gamma rays. And if the amount of gamma ray emitted from the rock is enough, then theoretically this could lead to splitting of formation water molecules in contact with the rock or near the rock into hydrogen and oxygen. Now, that so that process is known to exist. How common it is on Earth, we don't really know. Um, but we do know that rocks like uranium-rich granites are not enormously common. So therefore, this is not basically a thing that you could hope to encounter just anywhere on Earth where you look. Then the other process that is known to emit hydrogen is what's called lower crust degassing. So the concept there is that the deeper part of the crust and below that in the mantle and even towards the core of the Earth, uh, there's still a lot of hydrogen that uh, um, was basically trapped there during formation of the Earth, and where rocks are brought basically up from the mantle and the lower crust are basically being brought up to closer to surface, then they would degas and they would emit some of this hydrogen. Now, how much hydrogen would be emitted? Is it? Yeah, there's some estimates out there, but there's not a lot of hard evidence. And again, uh, um, bro- um, rocks that originated from the deeper crust or the mantle being brought to surface, those kind of settings are not extremely common. It's not to say that there are no such places, but it's like with the radiolysis. This is not something you can hope to encounter just almost anywhere on Earth you search.
Why is there a lack of information on flow rates in recent hydrogen findings in Mali and Nebraska? And how crucial are these rates for assessing viability?
Okay, flow rates for commercial development of any gas, whether it's now natural gas or hydrogen, are very important. And the reason for that is that to produce material quantities of gas, you either have to have lots of hundreds of thousands of wells producing at modest flow rates, but much more attractive is a lesser number of wells producing at very high flow rates. And you want material amounts of gas because commercial buyers of gas, like a power station or a steel plant, they want to secure, when they sign a contract to buy the gas, they want to secure delivery of material volumes for a reasonable stretch of time. They're not so interested to buy just a tiny little bit of gas. And similarly, investors in a gas project, whether it's now a natural gas project or a hydrogen development project, they would be looking for materiality and also for basically the ability to sign material contracts when they decide on committing to large investments in wells, infrastructure, and the like. So that is why flow rates are very important. Now,
Yeah.
why are information on flow rates from the recent hydrogen finds so scarce? I think it is because uh, um, in the places where there are some indication of flow rates, they're low. In
Yeah.
Mali, there are actually from some conference papers and some recent scientific papers that published, the paper in Nature, there are some flow rates and they're very low. This Buku 1 well, the shallow water well that encountered gas and was then hooked up to a power generator, it produces 1500 cubic meters per day of hydrogen. And that sounds like a lot, but it's actually very little compared to natural gas wells. It's it translates to about 3 barrels of oil per day, and typical oil wells or typical gas wells, they would produce hundreds or even thousands of that amount per day. In energy terms, 1500 meters cube per day is equivalent to about 70 gigajoule, which sounds per day, which sounds like a lot. But in power terms, it's 200 kilowatts, which is about less than a tenth of the power output of a typical onshore wind turbine. So it's actually very little. I
Yeah.
think this is the reason why people are not very forthcoming with flow rates from Mali. I mean, they have published it, but they're not basically shouting it all off the roof. In other
Yeah.
places, like for example in the find in France, and or the find in Aragon in Spain, or in Australia, I think in the Perth Basin. So far, no material amounts of hydrogen have been recovered to surface. So there, the hydrogen is what the geologists would call shows. So these are indications of gas inflow into the well during drilling of the well in the drilling mud, but without dedicated attempts, either by trying to flow the well or by taking lowering a sampling tool down the well, sampling the gas. And so trying to see now, can I flow hydrogen at material quantities from this well? This still needs to be done in the case of the France discovery and the Spain discovery and the Australia discovery.
Are there ongoing technological developments addressing the challenges in exploring subsurface hydrogen, and what advancements have been made?
Um, yes, there are ongoing technological developments. Um, um, Historically, um, exploration drilling, kind of globally, was focused on finding oil and gas and not hydrogen. And the uh, gas detection toolkits that are carried uh, historically in exploratory drilling is not even able to detect hydrogen. So now that there is more interest in natural hydrogen, um, uh, I anticipate that um, service companies are working on gas detections toolkits that could be deployed in exploration wells to look for hydrogen. And once these kits become available, I think we will see more um, reports of natural hydrogen from exploration drilling worldwide. That's not to say that now we will see lots and lots of it, but I think we will see more of it. In general terms, I think the since the world is now looking for hydrogen, or basically at hydrogen as a key element of helping to facilitate energy transition, I reckon that this interest will spur more development of technologies.
What potential geopolitical and environmental implications are associated with widespread hydrogen exploration, considering its impact on energy markets and emissions?
I talked about this a little bit already. It's a very good and very valid question, and I think it is something that uh, hasn't been brought to the public attention enough in basically talking about the potential of natural hydrogen. Is that the settings where the hydrogen has been found to date, which are basically these natural seeps uh, at very low pressure, like in Mali, or the hydrogen adsorbed in coals seen in France, and hydrogen in quite tight rocks, like in the southern Pyrenees in Spain. Uh, these settings would, uh, if they prove commercially eventually, they would uh, involve drilling lots of wells because the flow rates are likely to be low. And um, in, in in instances like the hydrogen stored in the coals, but also in the natural seep scenario where some of the hydrogen may actually be dissolved in water rather than be a free gas. Trying to produce the hydrogen would would uh, go with producing a lot of water, and this water is not uh, uh, nice and fresh. It's likely saline, and it could have traces of hydrocarbons and drilling fluids. So, treating this water and then disposing it in an acceptable manner is going to be a challenge, like it is in other cases of so-called resource plays, like coal-bed-methane and shale gas.
Can this water be reused for any purpose, agriculture or
Um,
something?
yes, it's potentially it can, but you would first have to desalinize it and get rid of any traces of hydrocarbons and drilling fluids. Like I have a lot of working experience with coal-bed-methane developments in Australia. And Australia is a very dry country, and there so water is scarce. And uh, the farmers, they don't like it if you basically propose to dump uh, um, excess water from coal-bed-methane wells in like an artificial lake or so. So you would have to treat this water to really, really high standards. It's not impossible, but it's quite costly. And
Yeah.
the economics of these projects is often so marginal that it can't really carry that cost.
Considering
It's not
the
to say that it's impossible, but
yeah,
it comes with a cost.
yeah. Considering the significant quantities of white hydrogen found in France and Switzerland, are there ongoing efforts to assess the global potential of natural hydrogen deposits, and how might this impact the energy landscape?
It's uh, it's a good question. I was very intrigued by this find in France, and I think I talked about it already a bit in some of the earlier questions. My personal view, based on information I've sourced from the open domain about what this find is, where they found the hydrogen, in what context were they exploring for it. I don't think this is gonna be a really easy exploitable discovery, and the reason is, like I explained before, this hydrogen is likely uh, uh, contained at the molecular level, adsorbed to coal crystal lattice, like mine gas in a coal bed methane. It's it's not surprising that the tests where this hydrogen was discovered were actually not done as a dedicated effort to look for hydrogen. No, they were done as part of a European project looking at potentially reviving the old mining district of Lorraine in France as a coal-bed methane development. And um, based on the information released to the public, you can see that the amount of hydrogen in the gas is actually not enormous. It's not
Mhm,
pure hydrogen.
mhm,
It's in fact the gas at shallower levels is mostly methane, with at shallower levels only a few percentage of hydrogen, and then deeper down the hydrogen content increases to about 12 or 14% at maximum. But that is basically at the depth of already a kilometer. And then
yeah,
in the press releases, statements were made about extrapolating this trend to depths of 2 or 3 kilometers, and then saying at those depths you would get nearly pure hydrogen. And and I mean this might be, whether or not that's true, which you can extrapolate like that, is already questionable, because the storage capacity of coals doesn't increase linearly with depth. But more importantly, producing gas from coals buried deeper than about a kilometer is technically extremely challenging, because the coals get very, very tight. The typical exploitation floor for coal-bed methane, which is kind of the logical analogy, would be
yeah.
7 to 800 meters, a maximum of maybe a kilometer. So that is why this find in France is going to be quite challenging to produce from the coals where the hydrogen contents are more substantial. And then another challenge is going to be to separate the methane from the hydrogen, because separation is it's technically possible, but it's not straightforward and it's going to be costly. My take
Mhm.
is that given that most of the gas, especially in the shallower coal, is actually methane and not hydrogen, commercialization of this project is going to hinge on the potential value of the methane, not the hydrogen. and a key factor is whether or not this development could be done in an environmentally acceptable manner, and which means disposing the water properly and uh, um, increasing flow rates from the wells by some sort of stimulation, but still getting regulatory approvals for
Hmm.
that.
There are mentions that the Earth has locations where conditions coexist to naturally produce and accumulate hydrogen. Could you provide examples of other regions where such conditions might be present?
Yeah, uh, I can try and do this. I talked about some of this already with in the earlier questions. So conceptually, there's really three type of settings where exploitable hydrogen might occur. One setting would be the so-called natural seepage settings, where somehow uh, hydrogen generated maybe from hydrothermal alteration of basement rocks, so the serpentinization, or maybe there's some radiolysis as well. But some hydrogen is generated deeper down in the subsurface from basement rocks, and somehow this hydrogen steepage, which is initially quite diffuse, would get focused into maybe major fault zones or some sort of permeability pathways. And then when you drill a well into a pathway like that, then you produce material amounts of hydrogen. I believe, based on all the data I've seen on that finds, the Mali um, hydrogen finds is an example of such a setting. You can produce from it, but getting high flow rates is going to be a challenge. Drilling cheap wells is going to be a key. Then a second setting, like is what I described for the France hydrogen find, which is hydrogen adsorbed in coals. And there, I think I talked about most of the key factors already, which is basically permeability. Coals are typically very low permeability, so to produce wells at high rates, you need to um, so-called stimulate wells by fracking them or doing what's called underreaming, so enlarging the well downhole, drilling horizontal wells into coal seams. These are all gonna increase costs, and some of them are technically a bit challenging. They may be environmentally challenging, and then the drainage areas of wells are going to be low, so I need to drill lots of wells, and littering, for example, the Lorraine landscape with hundreds of wells. Maybe uh, that's maybe what's required to commercialize a project like that. Which whether this is what people have in mind when they think about exploiting a natural emission-free resource and doing it in a green way, I'm not so sure.
What's your prediction on white hydrogen and its usage in the market and the role and let's say percentage it will have finally?
I reckon it a lot of it stands or falls with whether or not the ongoing exploration efforts, for example, the efforts in Spain, where there are in the southern Pyrenees, where they're re-drilling an old 1960s well in a place where some tentative hydrogen shows were recorded in what looks like it could be actually a proper trap. Now, if you can find places where hydrogen is trapped at much larger pressure in significant quantities, like typically in gas fields, then those traps could be exploited uh, and they could deliver material amounts of hydrogen at at good rates. I don't think this is going to happen everywhere. There's going to be very specific locations, but if these kind of locations are proven to exist, then in at some places you could decarbonize nearby steel plants or power stations or so. I think this is very possible. It's not a certainty. it depends on what the next wave of exploration is going to show. Then, uh, uh, um, in addition to that, I think it's quite conceivable that we will see more examples of producing hydrogen at small rates, like what they're doing in Mali, to just provide hydrogen to basically power maybe small villages in the outback in towns in the outback in Australia, or in maybe in some remote places in Africa, where now getting energy is quite involved. In Australia, in the outback, for example, you would have to power is typically generated with diesel generators, and so now I need to transport this diesel over large distances. Now, clearly, this is not very uh, this is not emission free. So if I can replace some of this with hydrogen, even if the hydrogen is produced at low rates, I think it's still great. So I think it's those kind of opportunities are likely to evolve. Whether or not a much more material decarbonization is going to be done using white hydrogen, uh, I'm not so sure. We will see.
And finally, your opinion on the current hydrogen hype and generally the role of hydrogen in the energy mix in the future.
A very good question. Now I'm going to stick my neck out a little bit, and it's I I reckon looking at the companies involved in hydrogen exploration so far, and making those press releases, I don't I don't see these companies as having the neither the financial muscle nor the skills and know-how and technology access to eventually commercialize this hydrogen. So I think these are small companies that are out there to try and and make interesting looking finds, that and then basically try either flip the asset or flip the company. So they try and and make gather enough data, and then selectively release information to the markets to make basically make it look like there could be a commercial project in the future, and maybe there could be, it's possible, but then they wouldn't be the ones to driving it all the way to commercialization. Others would come in. So so that's my take on the current situation. I'm not aware of any companies that have financial muscle and technical skills and know-how. So, for example, small to mid-size oil and gas companies, or companies that are basically have links to power industry, uh, um, that they're right now they're starting to um, take up hydrogen exploration licenses. Not yet. It could happen, but that's why I think we're very early days, and I think the hype that's generated is more by small companies interested in getting investors and flipping assets.
Arnout, thank you for being my guest today. It was my pleasure.
You're most welcome. I hope it was insightful enough.
Thank you.